Welcome to lecture 11 of circles. So, in this lecture we will start with deriving the condition for two circles to intersect each other. So, we will derive that condition with more rigor. If we recollect, in the previous lecture we had stated that if the distance between the centers of the two circles is less than the sum of the radius, and if this distance between the two centers is also greater than the absolute difference of the radius, then under this condition we had said that the two circles will intersect at 2 points, although we had not shown this rigorously. So, moving ahead, so if we recollect, we had said that if there are two circles S1 equal to 0 and S2 equal to 0, and let us say that the radius of this circle S1 equal to 0 is R1 and the center is this point O1, and let us say that this circle given by equation S2 equal to 0 has radius R2 and center at O2, then we had made this remark that if the distance between the two centers is less than the sum of the radius, and if it is greater than the absolute difference between the radius of the two circles. So, when this condition happens, then we said that the two circles will intersect at exactly 2 points, and we also said that if if this condition happens, then the two circles intersect at 2 points. We also said that if the distance between the two circles is equal to the sum of the radius, then the two circles touch each other externally at exactly 1 point. We also said that if this distance between the centers of two circles is equal to the absolute value of the difference of the radius, then in that case the two circles touch each other internally. So, we had also explained this through examples. So, we had drawn circles and shown how these conditions can arise, but we had not proven these statements formally or rigorously. So, we will try to do that now. So, let us say that these are the two circles. So, we have this is the equation of the circle, first circle given by S1 equal to 0 having center O1, and let us say that this is the other circle S2 equal to 0. So, in subsequent discussion we will assume that, without loss of generality, we will assume that the radius of the first circle is greater than the radius of the second circle, or it can even be equal to the radius of the second circle. Let us denote the center of the second circle by O2, and in that case then this line segment has length d O1 O2. This is one of the points where these two circles touch, will be denoted by P, and we will connect O1 and O2 to this P. Now, let us try to examine what happens if, or let us say under which conditions will it so happen that these two circles will touch each other at exactly one point. So, if we also again recollect our previous lectures, then let us say that the coordinates of this point O1, which is the center of this first circle, are A, B, and let us say that the coordinates of the center of the second circle are C, comma D. Then the length of O1P is obviously R1, length of O2P is R2, and let us say that the coordinates of this point P are denoted by x and y, and then we had also said that let us say that, so let us say that this green dotted line is parallel to the x axis, and so is this green dotted line also, and let us say that this angle of O1P with respect to the x axis, so this angle is theta. Similarly, the angle of O2P with respect to the green dotted line, let us say that it is denoted by phi. We also drop a perpendicular from O2 onto this green dotted line. So, this perpendicular, let us denote this point by M, where the perpendicular meets the green dotted line. It is clear that if we can write this point x, the coordinates of this point P can be written in polar form with respect to both the circles. So, when we write this point P, the coordinates of this point P in polar form with respect to the first circle, we see that x is equal to a plus r1 cos theta and y is equal to b plus r1 sin theta. Similarly, x and y can be expressed in terms of polar form with respect to the second circle, in which case x is c plus r2 cos phi, y is d plus r2 sin phi. And now we can equate this and this equation and this equation, whereby we get that a plus r1 cos theta is equal to c plus r2 cos phi and b plus r1 sin theta is equal to d plus r2 sin phi. Now, because we have assumed r1 to be greater than or equal to r2, what we will do is that we will take this a onto this side. So, we get r1 cos theta is c minus a plus r2 cos phi and r1 sin theta is d minus b plus r2 sin phi, and now we can square this equation and add them up. So, when we square these two equations and add them up, we get r1 square cos square theta plus square of this left hand side, r1 square sin square theta equals the square of this plus the square of this, which is c minus, so the square of this term is c minus a square plus r2 square cos square phi plus 2 c minus a r2 cos phi, and then the square of this particular term here is d minus b whole square plus r2 square sin square phi plus 2 into d minus b into r2 sin phi. And if we were to simplify that using the fact that cos square theta plus sin square theta is 1 for any theta, and similarly cos square phi plus sin square phi is also 1, we use that fact, then we get r1 square is c minus a square plus d minus b square plus r2 square plus 2 r2 into c minus a cos phi plus d minus b sin phi. Now, c minus a the whole square plus d minus b whole square. So, c minus a whole square plus d minus b whole square is nothing but the squared length of this, of the distance between the two centers, which, so this we can denote by d square, d O1 O2 square. And let us say that here we for this term we multiply and divide by d O1 O2, and thereby we get, we can put a d O1 O2 here, and then we put a d O1 O2 in these two terms. Eventually we get r1 square is r2 square plus d O1 O2 square plus 2 r2 d O1 O2 times c minus a by d O1 O2 into cos phi plus d minus b by d O1 O2 into sin phi. Now, let us see what are these two terms, these c minus a by d O1 O2 and d minus b by d O1 O2. If we go back to the previous figure, what we see is that if we focus on this right angled triangle O1 O2 M, then we see that O1 M is nothing but c minus a, O2 M is nothing but d minus b, and let us denote this angle MO1 O2, so which is this angle, let us denote it by alpha. So, it is easily seen that c minus a divided by d O1 O2 is nothing but cos alpha, and d minus b divided by d O1 O2 is sin alpha. So, if we use that, we get this to be cos alpha and this to be sin alpha, and therefore, we have this expression, but this is of the form cos a cos b plus sin a sin b, and this is nothing but cos of phi minus alpha. So, the it is also clear that the value of alpha depends on nothing but the coordinates of the centers of the two circles, which is given to us. So, alpha is known to us. Therefore, what is unknown to us is the value of phi and theta, because we don't exactly know the points of intersection of the two circles, and that is what our effort is to devise a method. Our effort here is to come up with a method to to characterize the points of intersection. So, the points of intersection were given by these two polar forms. So, the moment we are able to find phi, it is clear from either phi or theta. So, we have eliminated theta here. So, now what we have here, if we see this equation, we basically have a trigonometric equation in terms of phi. So, if we can solve, so this equation is precisely this equation, r1 square is r2 square plus d O1 O2 square plus 2 r2 d O1 O2 into cos of phi minus alpha. So, everything in this equation is known to us, because we know the equation or two circles. So, we know the radius, we know the distance between the centers, we know this angle alpha. Now, what is not known is phi, which we can know by solving this equation. Once we know phi, we can very easily put the value of phi here and we can get the coordinates of this point of intersection. So, from this equation, so from the previous slide we have cos of phi minus alpha is r1 square minus r2 square plus d O1 O2 whole square upon 2r2 d O1 O2. So, essentially we have to solve this equation to find the value of phi, which can be done graphically like this. So, we will plot cos of phi minus alpha on the vertical axis versus phi on the horizontal axis, and the graph of cos of phi minus alpha might look something like this. So, let us say this is alpha. So, when phi is 0, cos of phi minus alpha cos of phi minus alpha is cos of alpha, which is let us say this value. When phi is alpha, cos of phi minus alpha will attain its maximum value of 1. So, let us say we have something like this. So, this is one complete cycle. So, this value would be 2 pi, and this value of phi where it attains its minimum. So, we see that when if we have phi equal to alpha plus pi, then cos of phi minus alpha is minus 1. So, which is the minimum possible value it can attain, and it will attain that at phi equal to alpha plus pi, which is this point. Now, if it is clear that if this value on the right hand side of this equation has an absolute value which is less than or equal to 1, then we will have a solution. So, we can represent this value by a horizontal displacement from the x axis. So, let us use a green dotted line to. So, suppose if this value is let us say less than 1, suppose let us say it is equal to half. So, if this value is equal to half, so half is somewhere here because this is 1. So, this is half, and then corresponding to this value which is let us say half, we will draw a dotted line which is parallel to the x axis and is displaced from the x axis by half. So, the places where this green dotted line is going to cut the curve for cos phi, because this green line is geometrically the equation of the line y equal to this value for this graph. So, obviously, wherever this green line is going to cut the curve for cos phi minus alpha, these two values will be equal, and therefore, in this case if this were to be half, then the two values of phi would be this value and this value. In fact, it is easily seen that as long as this value on the right hand side has a modulus value strictly less than 1, if the modulus value is strictly less than 1, then one can easily see that there will always be two solutions of phi, because of this complete one complete cycle here. There will be two different values of phi which will satisfy this equation, and that will happen if this right hand side has an absolute value which is strictly less than 1. For example, we took half and then we saw this and this were two different values of phi. However, if this, so that particular case where this right hand side has an absolute value less than 1 will correspond to the scenario where the two circles intersect each other at 2 points, at exactly 2 points. However, we see that if this right hand side were to be equal to 1, either 1 or minus 1. So, if this right hand side is equal to 1, then the green dotted line is something like this, in which case the green dotted line corresponding to this value of 1 touches this curve at only one place, exactly one place, which corresponds to phi equal to alpha, and therefore, the two circles will touch each other only at one place, which whose coordinates are given by, whose coordinates will be given by this equation, but with phi equal to alpha. If this right hand side were, if the radius and the distance between the centers were such that this right hand side is equal to 1. Similarly, when it is equal, when this right hand side is equal to minus 1, even then when it is equal to minus 1, then the green dotted line is something like this, and even in that case there is exactly one value of phi which satisfies this equation, which basically means that there is only one point x y corresponding to phi equal to alpha plus pi, where these two circles will touch each other. So, in this special case where this right hand side is equal to 1 or minus 1, we see that the two circles will intersect each other at only one point, which basically means that they will touch each other at one point. So, next we will try to see how we will try to characterize these two cases where the circles touch each other in terms of this of R1, R2 and the distance between the two centers. So, we just now had said that, so let us say that R1 square minus R2 square plus d O1 O2 whole square by 2R2 d O1 comma O2 is equal to, let us say, minus 1. And let us see what this corresponds to. So, which is equal to cos of phi minus alpha. So, this will happen if and only if. So, if we try to just solve this, what we see is that R1 square is equal to R2 square plus d O1 O2 whole square minus 2R2 d O1 O2, which means that R1 square is equal to R2 minus d O1 O2 whole square, and this implies that R1 is either equal to R2 minus d O1 O2 or R1 is equal to d O1 O2 minus R2. Now, clearly this case is not possible because we had initially said that R1 is greater than equal to R2, and d, the distance, is always a non-negative quantity, the distance between the two centers, and therefore, this possibility is, this is not possible. So, the only possibility is this, and this condition is nothing but that the distance between the centers is equal to the sum of the radius. So, this is one condition in which the right hand side is equal to minus 1, but let us try to also geometrically see what does this mean. So, when the distance between the two centers is equal to the sum of the radius, this expression is minus 1, which means that cos of phi minus alpha is minus 1, or which basically implies that phi is equal to, so phi minus alpha is basically pi, or basically that phi is equal to alpha plus pi. So, what we have is that phi is equal to alpha plus pi. Now, if we go back to this figure, Let us see what it means when we say that phi. So, we have said now that phi is equal to alpha plus pi. So, we want to investigate this situation. So, let us see this angle. So, this angle here is so this is 90 degrees. This angle here is obviously pi by 2 minus alpha, and therefore, this angle O1 O2 P, O1 O2 P, this angle which let us denote by beta. So, this angle beta can be calculated because this is phi, this is 90, this is pi by 2 minus alpha. So, it will come out to be, so beta will come out to be pi beta equal to pi plus alpha minus phi. Now, when phi is equal to alpha plus pi, which is the scenario we are considering right now, then if we replace this phi by alpha plus pi, we see that if this happens, then beta is actually equal to 0, beta is equal to 0. But what does beta equal to 0 mean? So, let us now focus on this triangle O1 O2 P. So, beta equal to 0 means that, so this angle beta is going to collapse to 0, which means that this point P is on this this point P must lie on this somewhere in between the points O1 O2 on the straight line O1 O2. So, basically this triangle O1 P O2, so basically this triangle O1 P O2 becomes a straight line with the point P somewhere in between the points O1 and O2. So, this is what will happen when beta collapses to 0, when beta is equal to 0. And in that case, what this basically means is that, so what it basically, what this case basically, what this condition basically then means is that so we have O1 as the center of the first circle and we have O2 as the center of the second circle, and their point where they touch each other. So, these two circles touch each other at exactly one point, which is the point P, and this point P lies on the straight line joining the centers. This is what it means, and it lies somewhere in between the straight line joining the centers. So, in between O1 and O2. So, we have something like this. O1 O2, this is the point of contact P, and further if we, let us say at P, if we draw a perpendicular, so at P we draw a perpendicular to this straight line O1 O2. So, this perpendicular is this blue line. Then it is clear that the shortest distance between any point on this blue line and this center O1 of the first circle will be the perpendicular distance from the center O1 to this straight line, and that perpendicular distance is obviously O1P, because we have constructed this line to be at 90 degrees to O1 O2, and because O1P is the radius of the first circle, this distance O1P is equal to R1. Now, clearly if we take any other point on this blue line, then the distance of that point from O1 has to be strictly greater than R1, because the closest point to O1 was this point P, and we are now choosing another point on this straight line which is not P. So, hence it is clear that the distance of that point, of any other point apart from P on this blue straight line, will be more than this radius R1, and therefore, that point will lie outside this first circle S1 equal to 0. Similarly, we will show that any point, it is very easy, similarly it is very easy to show that by using similar arguments, that any point on this straight line apart from P will lie outside this second circle also, and therefore, all points of this straight line. So, and therefore, the only point on the straight line which touches both the circle is this point P, and hence this straight line is nothing but the transverse common tangent to both these circles. So, this condition D1 what we have just seen now is that if the two, so and this situation, if we remember our previous lectures, we say that whenever this happens, that the point of contact of the point where the two circles touch, if it lies between the two centers on the same straight line. So, if the point of the point where the two circles touch each other, which is this point P, lies on this straight line O1 O2, and between O1 and O2, then we said, when we say that these two circles touch each other externally. So, hence what we show is, what we have shown is that if the two circles touch externally, then it must be true that the distance between the two circles is R1 plus R2. So, this we have just shown now rigorously. However, what about the other reverse argument? Let us say that we are given two circles and it is said that the distance between the centers is equal to the sum of the radius. So, this is the reverse argument. So, it is said that the distance between centers is equal to the sum of the radius. Then does it mean that the two circles will touch externally at exactly one point P? That is indeed true, because if we start with this equation and if we put it in this expression here. So, we know that cos of phi minus alpha is equal to R1 square minus R2 square plus d O1 O2 whole square by 2 R2 d O1 O2. Now, in this equation, if we put this d O1 O2 to be equal to R1 plus R2 and do a little math, what we will see is that this value will come out to be minus 1. And then again this will basically mean that beta is equal to 0, which will mean that the two circles will touch each other at P. It is not very difficult to also visualize this, because as beta goes to 0, what will happen is that this arm and this arm will both start coming towards the straight line joining the centers. But this can only happen if we move this circle outside slowly. So, when we move the circle outside, then what will happen is that this angle beta will start reducing till we have moved it so further that there is exactly one point where these two circles will touch. In a similar manner, if we, and this can be left as an exercise for the students, in a similar manner, if we equate the right hand of this equation, in the right hand side of this equation equals to plus 1, because we have seen the minus 1 case earlier. If it equals to plus 1, then it is, we can show that from here, we can show that the distance between the two centers is equal to R1 minus R2. In our case, we have taken R1 greater than R2. So, therefore, this is in fact equal to the absolute difference of the radius. But then, if since this is equal to 1, the only solution is phi equal to alpha, and phi equal to alpha will correspond to, if we go back to this figure, when phi is equal to alpha, it corresponds to beta equal to pi. So, beta equal to pi means that this circle is moving inwards, so that this is moving like this. So, we can show that through examples. So, one scenario is when the circles are touching the circles are intersecting at 2 points, which is like this, in which case this angle is beta. Now, if the smaller circle moves further inside, then we will have a scenario something like this. So, this will be the centers, this will be the line joining the centers, and then so now this angle beta will increase. So, this will be the angle beta now. Earlier it was acute, now it has become obtuse, because this circle has moved inside. So, and when it so happens that the second circle moves so much inside that it just touches the bigger circle at just one point. In that case, what will happen is that this was the point P. So, in that case, what will happen is that this point P will come here, and it will so happen that O1, O2 and P will be on the same straight line, because this, when beta becomes pi, this triangle O1, O2, P will collapse into a straight line, but then the difference from the -1 case is that in the -1 case the triangle O1, O2, P collapsed into a straight line which was O1, P, O2. So, when we had the -1 case, if we see the triangle O1, O2, P collapsed into this straight line O1, P, O2 with P in between O1 and O2. Because P was in between O1 and O2, that is why we concluded that, and because P was between O1 and O2 and P is the point of contact of the point where the two circles touch. So, that is how we concluded that the two circles must be touching each other externally. But now, for this +1 case, what we see is that the triangle collapses into a straight line which is O1, O2, P. So, clearly this can only happen if the circle, the smaller circle touches the bigger from inside, because the point of contact or point where the two circles touch is not lying in between the two centers, it is on the same straight line, but when extended forward. When we take this straight line joining the centers and if we produce it further, then it actually meets P. So, P is outside the line segment O1, O2, although it lies on the same line, but it is not a part of the line segment O1, O2, and that helps us to conclude that the two circles must be touching each other internally, and this is the condition for that. And vice versa also, it is very easy to show. If we forget, if we just look at this equation, except we had put it to equal to 1, we had substituted this to be equal to 1 for the case where we wanted to see what happens, because we were interested in the two scenarios where we have only one solution, because when we have only one solution of phi, it basically means that the two circles intersect each other at only one place. Because if we go back to this slide, if we have different values of phi's, each different value of phi will correspond to a different point P, because if we change phi, then the x and y coordinates will change, which means that we get a different point of intersection. But we saw that in some special scenarios where so we saw that in special scenarios where this right hand side is either +1 or -1, in such cases there is only one solution of phi or one value of phi which solves the equation. There are not two values, there is exactly one value, and clearly one value of phi will correspond to exactly one point where the two circles will meet. which basically means that the two circles will touch each other at that point. And then we can also, for this case, we can, we start with this condition. If we start with this condition, then, and if we put this value over here, then what we will see is that this right hand side will equate to +1. So, which basically means that even if this condition is true, then that also means that the two circles touch each other internally. So, what we have shown now is that if the distance is equal to the absolute difference, then the two circles touch each other internally, and just prior to that we had shown that if the two circles touch internally, if the two circles touch each other internally, then it must be true that d over O2 is equal to the absolute difference. And something similar we had shown for the case where they touch externally. And then we had also seen in our previous lecture that the two circles are going to intersect each other either at 1 or 2 points. So, they will intersect at exactly 2 points if this right hand side has a magnitude which is less than 1. So, and that we had analyzed in our previous lecture. So, if the magnitude is less than 1, then the two circles intersect at exactly 2 points, and if this value has a modulus equal to 1, then two circles touch each other. And of course, if this value, the absolute value is greater than 1, then there is no solution of phi. If this value is greater than 1, if the absolute value of this is greater than 1, then clearly there is no solution of phi, because the range of the cosine function is between +1 and -1, which basically means that since there is no solution of phi, it basically means that the two circles do not touch each other, or neither do they intersect each other. The two circles do not intersect. And then a little bit of algebra. For this case, we showed that there were two cases corresponding to whether they touch externally or internally. And then this particular case is not very difficult to analyze, and I think in the previous lecture we had said that if d over O2 is less than R1 plus R2, and if it is greater than the absolute difference, if so this first case over here is exactly equivalent to this condition. So, we take up a little example just to illustrate what we did, what we have so far done in this lecture. So, let us say that we have two circles. So, let this be the coordinate axis x and y. So we have one circle whose center is at the origin and whose radius is, let us say, 3 units. So, the circle is something like this. So, this is the first circle, and let us say we have another circle S2 whose center is at this point, which is 5, 0, and whose radius is also, let us say, 3 units. So, this is the other circle. Both of them have the same radius, but the centers are at different centers have different coordinates. So, they intersect at these 2 points P and Q, and if we were to write down, so for these two triangles, this is O1, O2 and this is P. So, this is the triangle O1, O2, P that we get. R1 is 3, R2 is 3 and D O1, O2 is 5. So, in this case, for this case what we will get is that if we follow the same analysis that we had done for the general case, then what we will get is that cos of phi minus alpha will be equal to here our alpha is such that cos of alpha. So, this point is, we had earlier represented the center of the first circle by a comma b, center of the second circle by c comma d, radius of the first circle by r1 and radius of the second circle by r2, and the distance between the two centers by d O1, O2, which is 5 in this case. The radius are both 3 in this case. AB is the origin, CD is 5, 0. Cos of alpha was C minus A by D O1, O2, which for this particular example is going to be C minus A is 5. So, 5 upon 5 will be 1. So, cos alpha is 1 and sin alpha is clearly 0, because sin alpha was D minus B upon D O1, O2. So, that is what we have for this example. And cos of phi minus alpha was, we had the equation that it is equal to r1 square minus r2 square plus d O1, O2 square by 2 r2 d O1, O2. So, this will be equal to 3 square, which is 9, minus 3 square plus 5 square by 2 into 3 into 5, which will come out to be equal to minus 5 by 6. So, and then what we can do is that we can go back to our graph. So, of course, from here we also see that since cos alpha is 1 and sin alpha is 0, it follows that alpha is nothing but equal to 0 degrees, and therefore, cos phi minus alpha is nothing but cos phi itself. And to find this solution, or basically now that we want to find the coordinates of these 2 points, what can simply be done is that we have to draw a green horizontal line with a displacement of minus 5 by 6 from with respect to the x axis, but parallel to it. So, that is going to be something like this. So, this is 5 by 6 on the negative side. So, we see that this minus 5 by 6, this horizontal line minus 5 by with at a displacement of minus 5 by 6 from the x axis and parallel to the x axis cuts or intersects this curve for cos phi minus alpha at 2 points, and therefore, these are the two solutions of. So, these are the two values of phi, which will give us cos of phi equal to minus cos of phi minus alpha to be equal to minus 5 by 6. So, therefore, for this case what we have is that phi minus alpha will be equal to, so there will be two values. So, because it is minus 5 by 6. So, and in this case alpha equal to 0. So, we have to basically find the solutions to this equation cos of phi equal to minus 5 by 6. So, the of course, one value will be given by phi equal to cos inverse of minus 5 by 6, and this value of phi will belong to the interval 0 to pi. So, this first phi angle is essentially this angle. So, this is equal to cos inverse of minus 5 by 6, which belongs to, which is between 0 and 180 degrees, and the other value of phi will be equal to 2 pi minus this first value. So, let this be phi 1, this be phi 2, because we saw that there will be two solutions. So, we will denote this one by phi 1 and this one by phi 2. So, phi 1 is equal to cos inverse of minus 5 by 6. So, and phi 2 will be equal to 2 pi minus cos inverse of minus 5 by 6. And this angle 2 pi minus cos inverse of 5 by 2 pi minus cos inverse of minus 5 by 6 is nothing but, let us draw with so this other phi 2 corresponds to this value here, and that I will denote with this. So, that will basically correspond to this angle. So, from this line to all, starting from here all the way till this line. So, this angle in green is nothing but 2 pi minus cos inverse of minus 5 by 6, and as we can see this phi 2 will correspond to. So, now if we, so now basically by using these different values of phi 1 and phi 2 and using the polar representation of the point where the two circles touch, we know that x is equal to c plus r2 cos phi. So, let us say phi 1, and y is d plus r2 sin phi 1. So, when we put phi equal to phi 1 in the polar form, we get these 2 points. Let us denote them by x1 y1. So, this will correspond to, so phi equal to phi 1 will correspond to this point P, because this angle is phi 1 basically. So, this is phi 1, and this other angle shown in green is phi 2. So, the coordinates of this point P, which is this point, is x1 comma y1, which will be given by this equation, and this is not very difficult to calculate because we know all these values here. We already know phi 1, we know R 2 is equal to 3, we know that C is equal to 5. Similarly, we know D is equal to 0, R 2 is 3, and since we know phi 1, we can compute sin phi 1. So, we can basically compute the coordinates of this point. Similarly, to calculate the coordinates of this point Q, which let us denote by x2, y2. So, the coordinates of this point Q x2, y2 can be calculated in a similar manner, but it is just that instead of phi 1 we will have phi 2 there, where phi 2 is 2 pi minus cos inverse of minus 5 by 6. So, to be precise, we will have x 2 equal to C plus R 2 cos phi 2, and y 2 will be equal to D plus R 2 sin phi 2, where phi 2 is this angle. So, this was just a simple illustration of how we can use the techniques developed in this lecture to the technique that we developed was first used to essentially rigorously prove the conditions under which the two circles touch each other at exactly one point, and as a byproduct we also see that the same technique can be used to find the coordinates of the point of intersection of these two circles. And although in this example alpha was equal to 0, but in general alpha need not be equal to 0, but even in that case it is not very difficult, because what we will instead get here is that so instead of this phi here we would have had phi minus alpha, here we would have had phi 1 minus alpha, and here we would have had phi 2 minus alpha. So, if alpha was not 0, then the solution would have been phi 1 equal to alpha plus cos inverse of minus 5 by 6, and phi 2 equal to alpha plus 2 pi minus cos inverse of minus 5 by 6. So, in the next lecture we will start a new topic called family of circles, which will be something similar to what would have been discussed in the topic on family of straight lines. Thank you.